Welcome to this tutorial video. In this particular video, we'll be further analysing the data calculated or captured when we look at the energy changes in a mass spring system. Now, it's recommended you watch video 1 of the series before looking at this video number 2. So we have a free-falling mass in a spring, and it's extending out at different lengths till it eventually reaches the floor, or not the floor, but its full extension. And we're going to be looking at the various energy changes that occur. So again, just very quickly, here's the video that happens. 240 frame rate in the camera. It's falling down, the velocity is increasing, negative direction until it reaches the halfway point, maximum velocity of about 1.9 meters per second, at which point now the spring is stretching and velocity is decreasing. It's reducing to 1.6 the negative, to 1.4, etc. All the way to the point whereby at the end of this particular frame it becomes stationary and stops. Okay, you see here we've got a lot of data here in terms of position y, etc. And also you can work out velocity data as well from this. So I was able to download that from Tracker and place that in an Excel spreadsheet. So here's all the data for time, the x position, which is really relevant for what we're looking at because there's minimal movement in the left and right, but there is significant displacement in the y, the vertical displacement. From that, I was able to use the mass of 100 grams, or 0.1 of a kilogram, and the gravitational field strength of 9.8, multiply that by the vertical displacement, and I can work out my gravitational potential energy for every frame of that particular test or video. I can also look at the amount of height, or the displacement rather, as this travels along. So if we go back to our displacement graph, where are we? Our y, oops, not x, our y displacement, as that one travels, you can see that as it moves along, it's displacing with time. And again, we're collecting all the data here. So this is really it. This is the delta x from its reference position or its resting position that we can use to work out the strain potential energy. So those values that we had earlier with our y positions, we can use that to calculate the extension delta x. Okay, so all I'm doing is taking this away from the original height. So at the start there's no extension. As this drops, I'm taking it away from 0.665 to 0.663. So the extension now in the second frame is 0.02, and I can then use a half k delta x squared to work out the strain potential stored. So it starts off with no strain potential when there's no extension, and as it extends, it increases all the way down to the bottom, whereby just about all the energy is now transferred into the spring with strained potential energy. Also along the way, we can get data from our original tracker with velocity. Now velocity data here, we can use the mass again. Half mv squared allows us to work out the kinetic energy for each particular time of this journey as well. So we can look then at the sum of all the energy, and it is simply the gravitational potential plus the strain potential energy in the spring plus the kinetic, and that has been taken into consideration for all the time frames of this particular graph. Now that's a lot of data, more effectively looked at as a graph. This graph's got a lot of information. You can see at time 0, the blue chart here, plot represents the gravitational potential energy. So it's all gravitational potential at the point. If we go back to our original video, right at the start, you can see we've got no stretch in the spring, no elastic potential energy. There's no movement, means there's no kinetic energy either. So if we go back to our graph, that's why we've got all gravitational potential and no kinetic and no elastic potential. Okay, so that sums up to give us our total sum. At the far end, when it's fully stretched, what we have now is all strain potential energy, no kinetic, and because it's not moving, and no gravitational potential. So we go back to our graph, and you'll see at this point at the far end, it's now orange, all elastic potential energy, no blue gravitational and no grey kinetic. But when I add them together, we get pretty much the same total energy, the sum of the yellow. In the middle region here, if I go back to our video and look at the middle, if we could say around about here in the center, what we find at this point, we've now lost half our gravitational potential. We've gained some strain potential energy from a half k delta x, and we've also got some kinetic energy because it's moving. As you can see, that's our position, or if you like better, our velocities are maximum in the middle here. Okay, let's go back and look at this. So in the middle region, we've got quite a bit of elastic potential. We've still got relatively half of our gravitational potential, and we've got a fair bit of kinetic as well. So our middle would be about here. Okay. Again, added together, this gives us a constant total or sum of energy. So notice that the velocity is a little bit rough from our tracking data, so it's not as smooth as perfect, and that's why our total yellow energy, the sum of the gravitational, the elastic, and the kinetic, varies a little bit at the top, but you can clearly see when I sum any of these along any time frame, the total is about the same. I hope this visual representation allows you to understand the energy is in fact conserved at any point or time in this spring drop. Again, thanks for watching.